So VSG will be equal to VOV plus VTP, right? But in magnitudes form, right? So VSG will be equal to magnitude of VTP plus magnitude of VOV. Obviously VSG would be negative, positive, right? So 1 volt plus 1 volt, it means we have VSG as 2 volt, right? VSG is 2 volt. Vs is already given to us. So VSG is equal to Vs minus Vg, right? So 2 is equal to 5 minus Vg, right? How about Vg? Vg is 5 minus 2 is 3 volt. It means we must be having 3 volt here, right? So for 3 volt, we can find the values of Rg1 and Rg2, right? Any value. For example, 5 volt, 3 volt should be across this resistance, then 2 volts across would be across this. It means the ratio of these resistances would be 3 into 2. If we take this as 3 mega, this would be at 2 mega, right? And we can take other values. And how about the rest? We can find RD, right? So VD minus 0 divided by ID is RD, right? Simple Ohm's law. So maintain up to the point that VD exceeds VG by magnitude of VT. What is the meaning of this sentence? We have solved one part. We have find the values of RD, right? And RG1 and RG2. We have designed actually the circuit. Now the second part is what is the largest value? For example, if someone change this value from this our designed values, take these values same, but increase this value. So then how much value of RD if he increase but remains in the saturation region? We have to find this, right? So if we increase RD, what will increase? VD will increase, right? So VD will increase, it means VSD will decrease, right? Vs is 5. If you increase VD, for example, this time VD is 3 volts. So 5 minus 3, VSD is 2 volts, right? And 2 volts means what? If VSD is greater than or equal to VOV, we are in the saturation region. So here VSD is 2 volt, which is greater than VOV 1 volt. We are in the saturation region. So it means what would be the critical value of VSD? Is 1 volt is equal to VOV, right? So you can find the value of VD for this value, right? So VSD is equal to VOV or VSD is equal to 1 volt. Then what would be the value of VD is equal to what? Vs minus 1 volt. 5 minus 1 is 4 volt. So VD could be having a maximum value of 4 volts to be in the saturation region. This is the limit. And for 4 volt of VD, what would be the value of RD is 4 divided by ID, right? VD max would be 4 volt. So 4 divided by ID is 8 kilo ohm. So it means RD can be maximized to 8 kilo ohm to remain in the saturation region. If the user increase the value of RD more than this, it can go out of the saturation region and enters into the triode region. Okay, so here we have used these calculations. I selected these examples to show you how these simple things can help you to find the designing and other problems, right? So I selected some hard problems. Otherwise, you have seen that the analyzation is very simple. The best thing is you have the same current in IS and as IS and ID. So ID symbol is used, right? Coming to the next problem, consider the amplifier circuit in this figure. Please check the soft form of the book, 6th edition, given to you already. The transistor is specified to have VT N. N-type transistor seems to be VN, right? Lambda 0, VDD, RD, VGS. Here they said that for AC VGS is equal to 0 and hint VDS also 0. Fine. VOV, ID, VDS and AB. It means you are only considering the DC equivalent circuit. Maybe this diagram has a full amplifier diagram including the AC signals and capacitors. So if you open your capacitors, VGS, VDS all will be 0 and you have to find only the DC parameters. Same, right? And then what is the maximum symmetrical signal swing allowed at the drain? Right? Symmetrical means no cutoff or saturation is occurring. Same would be here. We have already discussed. Hence, find the maximum allowable amplitude of a sinusoid VGS. So how much VGS we can apply to have a symmetric output without clipping at the saturation side or at the cutoff side. And the crux is you have to do it yourself, right? By concerning the book, because this is a solved example. Now DC biasing, Q point and load line. So instead of introducing these things for a general problem, I used a specific problem to show you, right? I selected an NMOS circuit of this kind, right? VTVA early effect, right? VTN, right? Or NMOS. Neglecting the early effect, use ID and VOV this to operate this transient saturation. Then what must be the MOSFET's KN be? So here we have to find the KN, right? Use ID, VD, and other things, VOV to find KN. So ID is half KN, VOV square. VOV is given, ID is given, half is a constant, you can find KN, right? And what is the DC voltage at the drain? And find the value of VD. And then find RN and GV, right? So this part would be belonging to the AC analysis we will do later, but at this time for DC analysis we can consider these. But let me show you one thing. From your previous knowledge about BJT, can you tell me which configuration of this amplifier? We are having input at the gate, output at the drain, then it is a common source amplifier. And the source resistance is not bypassed. It means it is a common source amplifier with a source resistance similar. So go ahead, find the DC equivalent circuit. It would be this one, opening all the capacitors, right? And then find VG, same 2 volt here, voltage divided by no current flowing there. And then ID is given, VS, we can say ID into RS. RS is given, so multiply by ID is VS is 1 volt, right? And then VGS is equal to VG minus VS. VG is given, VS is given, so VGS is 1 volt. So VOV is VGS minus VT. The thing is, why we are finding this? They are already given us the VOV. They said that you have to verify that for this value of current, is it working in the saturation region with this value of VOV? And if it is so, then the next part is find the VN. And then the next part is drain voltage, and then so on, right? So we are verifying it. So we cannot use this value. We have to bring this value by other way around to say that yes, you are right. Okay, so that's why we are doing all these efforts. We have find VOV ourselves for other values, ID and VG and other circuit parameters. And VOV is found to be 0.3 volt. It means it is verified, right? That for this current and these resistance values, this potential, we are having VOV as 0.3 volt. So now to find the VD, Kirchhoff's voltage law, why we are doing this? We can find VD directly, right? 5 minus this is equal to this, right? This multiplied by ID, and we can find this value. But I am doing the whole DC analysis, load line also, drawing the load line. So it means we can have an output load line here, right? So VDD, IDRD, VDS, ISRS, right? ID is IS, so it means VRD will be IDRD and VRS would be IDRS, not IS. So VDS, right? So again, we can rewrite this formula for ID, right? Common, and then ID is equal to minus this. And what is this? This is a linear equation. Y is equal to mx plus c. The same things we did for BJTs, right? So this is the load line. And if you draw this load line on the output characteristics curve, which curve? Common source curves, right? So in common source curve, x-axis has this parameter and y-axis has this parameter. So we can draw this line on the characteristics curves, right? So this will give us the extreme values of the characteristics curve. For example, VDS cutoff will be equal to what when ID is equal to 0? So VDS cutoff will be equal to, if this is 0, this whole decimal will be going, denominator will be going to multiply with 0 and then VDD. So VDS is equal to VDD. And for saturation, VDS will be nearly equal to 0. We can put it 0. Then ID saturation will be equal to this one. Same. This is the output. 1 up minus 1 by R out, right? The slope, sorry, minus 1 by R out. Value would be positive. So this is the saturation point. This is the cutoff point is equal to VDD. VDS is equal to VDD, right? And if it is working in saturation region, so you could be having a Q point here, not in the triode region, right? If you bias your transistor accurately. And how about VDS? For the given values, we have found VDS is equal to 1.5 volt. So we can find VD. They asked us to find VD. So DC analysis, DC biasing, Q point and load line. Finding of Q point is VDS, ID. ID is given, VDS we have found, so this is the Q point we can draw here. Load line, we can find the extreme values and plot it down, right? So before we go for the AC analysis of this circuit, let's just complete the DC analysis whole, right? And then when we introduce the AC analysis part, then we will reconsider this problem for the remaining AC related parameters, right? So biasing a MOSFET would be the same as we did for BJT, but the main benefit is there is no IG. It is less energy consuming device, right? No IG, right? And more simple because same current is flowing from RD and RS. Okay? So this is the voltage divider bias as we did in BJT and now introduced for MOSFET in the previous slide. This is the dual supply version, right? Same thing we did previously, right? We had RB here, now we have RG here. Large drain to gate resistance, right? Previously it was collector to base resistance, right? Here using a constant current source. This constant current source and this constant current source can be implemented by using this circuit. Okay, so these are all the same.